Hey guys, so in this video I want to introduce two properties of conservative forces that you may need to know conceptually, but that you're definitely going to have to know in terms of problem solving. Let's check it out. So first of all, remember that there are two types of forces. Forces can be conservative and non-conservative. The two types of conservative forces that we have are spring and weight force, or the force of gravity. Now, conservative forces have two key properties, and these properties are actually equivalent. They're the same thing, just looked at in different ways, or one leads to the other. Anyway, the first one is that the work done by conservative forces does not depend on the path taken. This is very important conceptually and for problem solving. Therefore, we say that the work done by conservative forces is path independent. You might see that your professor talk about that, or you might see that in a test. So the work done by conservative forces does not depend on the path, it's path independence. Okay, that's why I put that in here, that conservative forces are path independent. Weight is a conservative force, I just talked about that. So its work depends only on the vertical displacements and not on the path taken. So let me show you an example real quick. Here, let's say that all of these blocks are exactly the same mass, exactly the same thing, and they start from the same heights from rest. But they're going to fall in different ways. They're going to take different paths to go from this point to this point. First block is going to fall this way. Second block is going to fall this way down an inclined plane that has an angle of theta 1. This is a different inclined plane that has a different angle, theta 2. And then this block is going to go this way and get to the bottom. This one is going around a curved path like this. And this one here is going to start here. And I'm just going to draw a crazy path. Let's say it somehow moves this way and then it gets to the bottom. All right. In all of these cases, because all of these objects dropped the same exact height, they will all have the same final speed. Okay, and that's because the work done by the weight force, which is what causes the objects to speed up, is path independent. In fact, I can show you using the conservation of energy equation. Kinetic initial, potential initial, work non-conservative, kinetic final plus potential final. If you start from rest, this is 0. You have a height, so this is not 0. The object is falling at the absence of air resistance, so there is no force, no work done by you, and no work done by friction, so that's 0. Kinetic energy at the end, we have it because right before you hit the ground, there's a final velocity there, and the potential energy at the bottom is 0. So if we simplify this, we get mgh equals half mv squared. And the masses cancel. You can see that the final velocity equals the square root of 2gh final, which is something we're going to see quite a bit, this equation here. So it's a very usual answer for a lot of problems where something's falling. Notice that it depends on the height and not on the actual length of this arrow, right? So this squiggly line here is longer than this line here, the straight line, but it doesn't matter. All that matters is the heights. Okay, so that's a really important point. We're going to see that a lot in problem solving. The second one is that the net work done by conservative forces is 0 in a closed path. Sometimes this is also referred to as a closed loop. Okay, the total work done by conservative forces in a closed path is zero, and that's why it's part of the reason why they're called conservative, because if you do something and then you move the object but bring it back to the beginning, you didn't actually change the total makeup of the energy of the system. Weight is a conservative force, so I'll give you an example here on how the net work will be 0 if I start at A and then I move this box all the way, some object all the way around back to A. So imagine that this is you moving something sideways, and then you pick it up from the floor, lift it to this height, then you move it to the left, and then you drop it back to the floor, and it's back at the same point A. Okay. When you move this thing sideways, the work done by gravity or by the weight force is 0 because you're moving perpendicular to the weight, right? So you're moving this way, the weight force is this way, and because this makes an angle of 90 degrees, the work is 0. When you move something up, remember the work done by mg is the negative of the change in potential energy. In other words, the work done by mg is negative mg delta H, which means that if you, because of this negative here, if you're going up, your delta H is positive. Positive with a negative means that if you're going up, your work by gravity is negative, right? Also because another way of thinking about this, if you remember, is that if you're going up, gravity is pulling you down, so gravity is going against you, okay? Anyway, so when we go here, the work done by mg is negative. When we go this way, the work done by mg is also 0. Again, because it's perpendicular. Another way to look into it is that the change in height is 0. And then for this piece here, gravity does positive work because it works in the direction of motion. All right. So if I want to find the network would be the work done by the work that took place in each one of these intervals. So I'm going to call this 1, 2, 3, 4. There's no work at 1 and 3. And the work done at path, the leg number 2 over here, would be negative mg delta H, and for W4, which is this part here, it's positive mg delta H, and you can see hopefully that this is 0. The forces cancel. So the idea is whatever energy you had here, if you do some crazy thing and you come back here, as long as the force that's moving this thing around is the weight force, then you are a conservative force, okay? I'm sorry, the network would be 0 because it's a conservative force. Cool. Friction, however, is not a conservative force, so the network will not be 0, okay? Because the network is only 0 for conservative forces. So, for example, if you move object from point A to B and back to A, the network will be work 1 plus work 2. 1 is when you moved it that way, 2 is when you moved it back. The work done by friction, remember, is negative Fd, and it's always opposite to motion, right? So work net, let's move it over here, work net would be negative F1 d1 plus negative F2 d2. These two negatives combine, and the frictions will be the same. Friction is mu normal or mu mg, and just to show you that the same floor, so the same mu, same mass, same gravity, so the frictions are the same. The distances are the same as well. One's to the right, the other one's to the left, but it's distance. It doesn't matter the direction. So what I have here is you actually have negative Fd minus Fd, so negative 2Fd. Instead of canceling, they combine and they're both negative. This is clearly not 0. So in the first situation, if you moved, you would be back at the same energy. No energy is wasted in this process. But here, you're wasting energy moving this way, and you're wasting energy moving this way. All right? That's the idea. Having said that, I want to show you some practical applications of the first idea, which is that the final velocity, when we're calculating final velocity, really anything with energy, what matters is not the path taken, but the amount of height or the amount of vertical displacement. So let's get started here. So I have a mass of 2 kilograms. A block of 2 kilograms is released from the top of a smooth inclined plane. Smooth means that friction will be 0. That is 10 meters long and it makes 37 with the horizontal. Let me draw this. So 2 kilogram block. The angle is 37. The plane has a length of 10 meters. And I want to know what is the speed of this thing at the bottom here. So what is the final speed? The initial speed will be 0 because it's released from rest. Let me put that in here. And we're going to use the conservation of energy because I have a problem where an object is changing speeds while also changing heights. So the energy equation is a good one for that. Ki, Ui, work non-conservative, Kf, Uf. There's no kinetic energy at the beginning because the speed is 0. There is potential energy because you have a height. The work done by non-conservative forces is the work done by U plus the work done by friction. You didn't do any work. You released this block and you're just watching. And this is a smooth plane, so there is no friction. So this doesn't exist. There is kinetic energy at the end. And because we have a speed and we're looking for that speed, and the potential energy is 0 because when you're at the bottom, you are at a height of 0. So this is mgh initial equals half mv final squared. I can cancel the masses, and the final velocity will be the square root of 2gh, which you should be familiar with, right? This is going to show up a lot, I mentioned. The thing here is we don't have the heights, right? And by the way, this shows us real quick that it depends only on the height, right? But the problem is we don't really have the height. We have the length of the plane and we have the angle. Well, on a triangle, whenever you know two things from a triangle, you can find the other two. What I mean by two things is you have the, let's say the angles here, you have adjacent, opposite, hypotenuse. As long as you know 2 out of these 4, you can find the others by using either the Pythagorean theorem or SOHCAHTOA. But I'm just gonna remind you of this shortcut here. If you know the length here and you know the angle, the height is simply L sine of theta. Okay, so if you didn't already know this one, this is a good one to remember because it's going to show up a lot in these plane problems. They put this a lot to make sure that you know how to convert from when you're given L and theta instead of H, which is what you need here. Okay, so let's plug it in. The initial height is the length of this thing. It's all the way at the top, so it's 10 meters sine of 37. So the initial height is 6. Okay, so let's plug that in here, and then we're done. Square root of 2, gravity is 10, and the initial height is 6. So the answer here will be 11 meters per second. Okay, that's it for this one. Very straightforward. Here I have something that's I have a practice problem for you guys. It's a little bit different. Instead of a block coming down, it's going up the hill. I'm going to draw this for you just because it's a little sometimes confusing what exactly this means. But a block reaches the bottom of an inclined plane with 20, right? So when I say that a block reaches the bottom of an inclined plane with a 20 meters per second, it could mean that you're reaching the bottom going up, or it could be that you're reaching the bottom on your way that way, right? In this case, I'm asking how far up the plane will the block slide, which implies the block got to the bottom and now it's going to go up. Okay, so the block's here, and I want to know how far up the plane does it go. Okay, and it gets here with an initial velocity of 20. I won't put anything else. I just wanted to help you a little bit here. Let's give that a shot.